Class 11th chemistry, we were discussing unit 7 equilibrium, and in this video we will discuss about common ion effect. Common ion effect in the ionization of acids and bases. Let us consider acetic acid dissociation equilibrium, which is represented by this equation CH3COOH converting into H plus CH3COO minus. Acetic acid can also be written like this HAC, okay, where this AC is the CH3COO acetate, and this dissociate to give H plus and acetate ion. And for this equilibrium we can write acid equilibrium constant, that is Ka, concentration of hydrogen ion multiplied by concentration of acetate ion divided by concentration of acetic acid. Now in this equilibrium, if we add one of the product, then what will happen? Addition of acetate ions to an acetic acid solution results in decreasing the hydrogen ion concentration. Also, if hydrogen ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, that is in a direction of reducing the hydrogen ion concentration. This can be explained on the basis of Le-Chatelier's principle. That is, when we add one of the product, then reaction will proceed in that direction which reduce the concentration of product. So we can say reaction will go in the reverse direction. This can also be explained if we compare the QC and KC. When we are adding the one of the product, then QC becomes greater than KC. Okay. So reaction will proceed in reverse direction. So when we consider the ionization of any weak electrolyte, in this case this acetic acid is a weak electrolyte, okay, and at equilibrium if we add any ion which is common to this, then equilibrium will shift in the reverse direction. So we can say separation of ionization of weak electrolyte in the presence of a strong electrolyte having an ion common is called common ion effect. Okay, so we can say in acetic acid, if we add the sodium acetate, so ionization of acetic acid will reduce. In the same way, in acetic acid, if we add the hydrochloric acid, again ionization of acetic acid will be reduced. So this can be explained, and common ion effect is a phenomena which is based on the Le-Chatelier's principle. Now we will discuss the pH of the solution resulting on addition of a 0.05 m acetate ion to 0.05 m acetic acid solution. Actually, with the help of this numerical problem, we are trying to understand the common ion effect. Okay. Now in this case, we are taking the acetate ion, and these acetate ions are present in acetic acid solution. What effect we will observe? Again, we will discuss the acetic acid dissociation equilibrium, which is represented by this equation. Initial concentration of acetic acid is given 0.05 m. Okay, and in this case, initial concentration of acetate ion is also given, that is 0.05 m. And if change in concentration to reach the equilibrium is x, then we can say the concentration of acetic acid is decreased by x, and concentration of H plus and AC minus, that is acetate ion, will increase by x. So at equilibrium we can find out the concentration of acetic acid, that is 0.05 minus x, concentration of hydrogen ion is x, and concentration of acetate ion is 0.05 x. Okay, now we can write acid equilibrium constant, this concentration of hydrogen ion, concentration of acetate ion divided by concentration of acetic acid. Put the value. Hydrogen ion concentration at equilibrium is x. We can say concentration of acetate ion at equilibrium is 0.05 plus x, and equilibrium concentration of acetic acid is 0.05 minus x. And for acetic acid, which is a weak electrolyte, the acid dissociation constant is 1.8 into 10 to the power minus 5, which is very small. So we can ignore x in comparison to 0.05. So we can write 0.05 plus x is almost equal to 0.05 minus x, and which is almost equal to 0.05. So put all these values in this acid dissociation constant Ka. 1.8 into 10 to the power minus 5, this is equal to, now when we ignore this x, okay, so we will get this x multiplied by 0.05, this one. In the same way, in the denominator, if we ignore this x, so we will get this is 0.05, and if we calculate, we will find out x is equal to 1.8 into 10 to the power minus 5, and this x is actually hydrogen ion concentration. So this is equal to hydrogen ion concentration. And if we know the hydrogen ion concentration, we can find out pH. pH is equal to minus log of hydrogen ion concentration. Put the value of hydrogen ion concentration, find out the log, and we will get the final result, that is 4.74. Okay, now this is the hydrogen ion concentration in the presence of acetate ion, which is obtained from a strong electrolyte, and this is the pH in that condition. Now if we consider, or if we calculate the hydrogen ion concentration and pH if only 0.05 acetic acid solution is present, then this is only 0.05 acetic acid solutions there, then we can find out alpha, degree of dissociation for acetic acid, and that is equal to square root of Ka by C. Put the value. Ka is 1.8 into 10 to the power minus 5, and C is 0.05, and if we solve it, we will get 1.9 into 10 to the power minus 2, and in this equilibrium, hydrogen ion concentration will be equal to C alpha. Then C is 0.05 and alpha we have calculated, so hydrogen ion concentration will come 9.5 into 10 to the power minus 4. Now just compare this hydrogen ion concentration when acetic acid, only acetic acid is present, and this is the hydrogen ion concentration in the presence of acetate ion, which is added. So we can say in the presence of acetate ion, the ionization of acetic acid is decreased, so concentration of hydrogen ion is also decreased. Okay, and again if we compare the pH, then pH of only 0.05 acetic acid will come 3.02, but when we find out the pH of 0.05 m acetic acid in the presence of 0.05 m acetate ion, this will come 4.74. As the hydrogen ion concentration decreases, pH will increase. So we will understand the common ion effect with the help of this question. There is one more question. Problem 7.24. Calculate the pH of a 0.10 m ammonia solution. Okay. Then calculate the pH after 50.0 ml of this solution is treated with 25.0 ml of 0.10 m HCl. The dissociation constant of ammonia, that is Kb, is given 1.77 into 10 to the power minus 5. First of all, we will calculate the pH of only 0.01 m ammonia solution, and the equilibrium in that solution can be written like this: NH3 plus H2O converting into NH4 plus OH minus. Okay, and for this we can find out the degree of dissociation or degree of ionization. Alpha is equal to square root of Kb divided by C. Kb is given, and C, that is concentration of ammonia, is also given 0.10. So this C alpha is 1.33 into 10 to the power minus 2. And if we know the alpha, we can find out the hydroxyl ion concentration, which is equal to C alpha. Again, C is the concentration, alpha we have calculated, and this will come 1.33 into 10 to the power minus 3. Now with the help of this hydroxyl ion concentration, we can find out pH. There are the two ways to find out the pH. First of all, we use this formula. POH is equal to negative log of hydroxyl ion concentration. Put the value of hydroxyl ion concentration, take the log, and if we solve, we will get 2.88. This is POH. And from that, we can find out pH is equal to 14 minus 2.88, that is 11.12. We can also use another method. From this hydroxyl ion concentration, by using ionic product of water, we can find out hydrogen ion concentration directly. And again, we use the formula pH is equal to negative log of hydrogen ion concentration. We will get the same result. Okay. Now, this is the pH of 0.10 m ammonia solution. Now, we have to calculate when 50 ml of this solution is treated with the 25 ml of 0.10 m HCl. Now, ammonia is basic in nature and we are adding the HCl. So, some neutralization reaction will taking place. Let us see. Now, we are calculating the pH after 50 ml of this solution is treated with 25 ml of 0.10 m HCl. So, first of all, we have to find out number of moles of ammonia and number of moles of HCl in the given solution. So, number of moles of ammonia in 50 ml of 0.10 m ammonia solution is this. Now, how can we find out? Actually, what is the meaning of this 0.10 m? It means 0.10 moles of ammonia are present in 1 liter. That is 1000 milliliter of solution. So, how many moles of ammonia will be present in 50 ml? We will use this. That is 0.10 divided by 1000 multiplied by 50. So, we will get 0.005 m moles. In the same way, number of moles of HCl in 25 ml of 0.10 m HCl is 0.10 divided by 1000 multiplied by 25. Same way, that is 0.10 m HCl means 0.10 moles of HCl are present in 1 liter. That is 1000 milliliter of solution. So, how many moles will be present in 25 ml? If we solve it, we will get 0.0025 moles. Okay, now when we are mixing these two solutions, so we will get the net volume will be 75 ml. Okay, and some neutralization reaction will taking place. So on mixing both solution, 0.0025 moles of HCl neutralizes 0.0025 moles of NH3. Okay, we can say number of moles of NH3 is 0.005. Out of 0.005, 0.0025 moles of this is neutralized by HCl. Okay, so we can say the resulting 75 ml of solution contains 0.0025 moles of unneutralized NH3. And when NH3 react with the HCl, okay, then 0.0025 moles of ammonium ions will be formed according to this equation. NH3 when react with HCl, it will form NH4Cl plus Cl minus. Okay. Initial concentration, we are not writing in mole per liter. Simply we are writing the moles. For ammonia, this is 0.005. For HCl, this is 0.0025. Okay. When we mix these two, then at equilibrium, it's we can say for ammonia 0.0025 moles are neutralized. So remaining moles are 0.0025 moles of ammonia and 0.0025 moles of ammonium ion will formed. Okay. Now if these moles are present in the 75 ml of solution, so we can express in mole per liter, and that will come 0.033 molarity of NH3, and same for ammonium ion, 0.033 mole per liter of ammonium ions are present at equilibrium. Okay. Now this equilibrium, that is after the neutralization. After the neutralization, excess NH3 is present, and this NH3 exists in the following equilibrium: NH3 plus H2O converting into NH4 plus OH minus ion. Okay. Now initial concentration we already calculated for NH3. This is 0.033 m, and this is the initial concentration of ammonium ion, 0.033 m. Now again, if we assume that change in concentration to reach new equilibrium, that is Y. So minus Y is decrease from NH3 and plus Y of NH4 plus form, and in the same way plus Y of OH minus ion will form. So at equilibrium, concentration of ammonia will 0.033 minus Y. Concentration of ammonium ion is 0.033 plus Y. Actually, this is already present, and this Y is obtained after the ionization of ammonia. Okay, and concentration of hydroxyl ion at the equilibrium this will be equal to y. So we can find out Kb, base dissociation constant for this equilibrium. This is the product of ammonium ion concentration and hydroxyl ion concentration divided by concentration of ammonia. Put the value. Okay, and this Kb is equal to 1.77 into 10 to the power minus 5. Now again, this Kb is very less for ammonia. So what will happen? So this y and this y can be ignored in comparison to this 0.033 and 0.033 of this. So we can write 0.033 plus y is almost equal to 0.033 minus y, and that is almost equal to 0.033. Okay, so if we find out the value of y, it will come 1.77 into 10 to the power minus 5. And this, what is this y? Y is this hydroxyl ion concentration. So we will get hydroxyl ion concentration. Okay. Now, if we compare this hydroxyl ion concentration when no ammonium ion is present, so we already calculated that was 1.33 into 10 to the power minus 3. Now just compare this one and this one, which is smaller. This one is smaller. So we can say in the presence of ammonium ion, the ionization of ammonia is decreased according to common ion effect. Okay. Again, we can also find out the hydrogen ion concentration from this hydroxyl ion concentration using ionic product of water, that is 10 to the power minus 14 divided by 1.77 into 10 to the power minus 5, and this will get hydrogen ion concentration. And using this hydrogen ion concentration, we can calculate pH. pH is minus log of hydrogen ion concentration. Hydrogen ion concentration is this. Take the log of this and we will get this 9.25. Okay. Thank you.